Hi, and thank you for listening to my talk. Today I'll be speaking on refining economic arguments for grid-scale energy storage technologies, assessing the levelized cost of vanadium redox flow batteries. My name is Kara Rodby, and I'm a PhD student here at MIT in the Chemical Engineering Department under Professor Burchett. We're all aware that grid-scale energy storage is becoming increasingly more interesting and feasible as a method for adding reliability, flexibility, and sustainability to our energy system. Particularly as we seek to decarbonize our grid to greater and greater extents by adding more intermittent renewables, we're going to need to provide energy and energy storage for a vast range of grid services that all rely on different characteristic power and energy demands and are used at varying frequencies, such that we're going to need a diverse set of storage solutions, which is exemplified in this figure. So for example, uninterruptible power supply must be delivered rapidly on the scale of seconds to minutes, whereas more predictable, larger loads such as bulk power management can be delivered on slower timescales. This figure also exemplifies the range of potential storage technologies that can fit each need. So suitability of a particular battery technology for a particular application is going to be dependent on the unique technical attributes and the economic evaluation of the battery under the specific use case. And so we see flow batteries are one suitable solution for long duration applications. So this suitability is due to the unique decoupling of energy and power in flow batteries that's facilitated by its open architecture, in which the electrolyte or the capacity holding liquid material is pumped from external reservoirs through the reactor where the electrochemical reactions take place. And so with such a design, you can independently scale the energy capacity and the power rating of the battery to meet virtually any duration, though these systems do tend to be more cost competitive on a capital cost basis at longer durations, which is to say relatively large capacities. So while much attention has been given to lithium ion for grid storage because of its already relatively advanced development, because of the 90s with electronics and more recently with EVs, lithium ion may not be a cost competitive solution for all grid services, particularly these emerging longer duration needs. As a closed system, it can only be designed for a limited range of durations and thus has a fixed capital cost. The vanadium redox flow battery is the state-of-the-art flow battery chemistry with global installations approaching the gigawatt scale. Vanadium is a relatively expensive active material, though, that experiences large price volatility, making it potentially unattractive from an upfront cost standpoint. The reason the vanadium flow battery is the most researched and developed flow battery chemistry, though, is because of the fact that the long-term operation and maintenance costs for this system are so low. This is because vanadium has 4 stable oxidation states that allow for a relatively high voltage symmetric chemistry, meaning that both electrolytes have the same fundamental composition, such that undesirable crossover of the active species that leads to the capacity loss we witness in flow batteries does not actually lead to electrolyte cross-contamination and is fully reversible. So here's a simplified representation of a vanadium cell with vanadium 2,3 species on the negative side and 4 or 5 species on the positive side. To exemplify what this symmetric chemistry really means in terms of capacity loss and recovery, here we will go through an example. So over time, some vanadium will undesirably cross the semi-permeable membrane, which reduces capacity. Because the two electrolytes are of the same fundamental composition, with the main difference just being the average oxidation state of the vanadium in each electrolyte, we can regain the losses by performing rebalancing, which is transferring electrolyte between the two reservoirs until the number of vanadium ions between them is balanced. Besides the slight time this takes, though this process can be fully automated, the only cost is the energy to recharge the cell after the losses that are endured by the self-discharge upon crossover. Thus, it is a very low-cost remediation method that can be done essentially indefinitely. The other main driver of capacity loss after crossover in vanadium flow batteries and many other aqueous chemistries is side reactions, of course. These parasitic losses take electrons from the system and cause the capacity to be off balance between the two reservoirs. To exemplify this, in the case of vanadium, upon charging, V4 is oxidized to V5, while V3 is reduced to V2. But sometimes hydrogen is reduced on the negative side instead of V3, evolving hydrogen gas. This leads to an imbalance in the oxidation states, with some V3 left over on the negative side with no V4 to balance it on the positive side. So the V3 is no longer accessible capacity, and nor will this be recovered upon rebalancing as the average oxidation state is shifted here. That being said, this type of loss can also be fairly easily and cheaply remediated in the vanadium system. One common method for doing that and adding electrons back into the system is via a cheap chemical reductant. So oxalic acid is often used for the vanadium system because it selectively reduces V5 to V4, which restores the average oxidation state and thus all of the capacity lost to side reactions. The reaction does create water though, which can dilute the electrolyte and cause problems down the line, but the need for the remedy is on such a long time scale that this has yet to really be an issue witnessed in the field. Another method to maintain the oxidation state without any dilution would be to utilize a secondary cell to reduce the V5 or the V3. So in summary, flow batteries minimize maintenance costs because of the open architecture that allows for targeted component replacement or remediation, unlike a closed system like lithium-ion that requires augmentation or full module replacement to regain capacity. Vanadium flow batteries then take this a step further with their symmetric chemistry by eliminating cross-contamination and allowing for rebalancing. This has been the main driving force for the advanced development of this chemistry over others, and yet the economic benefits of this unique resiliency have really not been captured or quantified. So if we want to advance new electrochemical technologies targeted for grid services, we need new methods of technoeconomic assessment beyond capital cost, because capital cost does not capture long-term dynamics in cost and performance. Levelized cost of storage does, however. Levelized cost of storage is the sum of the discounted costs over the lifetime divided by the sum of the discounted energy stored over the lifetime. There's many variations of how to model this and what equation to use, but in our model, we've chosen to include upfront costs and the taxes and loans on those costs, as well as the ongoing costs, which are particularly the operation and maintenance costs and the charging costs. The energy stored is also a dynamic quantity as a result of capacity fade and recovery. We modeled the dynamic capacity in a fairly simple way, but that still includes the complexity of the decay and recovery components. So this schematic is meant to visualize the capacity model, starting of course at 100% of capacity. We assume linear capacity fade over time at about a cycle a day. So once the capacity decays to some lower limit, which is likely dictated by the battery's capacity rating, rebalancing will occur. This restores crossover losses, but not all of the capacity fade because some of that was lost to side reactions. So this process will repeat while the maximum achievable capacity from crossover is decaying linearly, which is to say hydrogen is evolving at a constant rate. Eventually, our accessible capacity, even upon rebalancing, will approach our lower limit, at which point we perform servicing by adding chemical reductants to rebalance the system. This process repeats throughout the operational lifetime. Now getting into some of the key results from this work, we performed some sensitivity analyses and found that in this model at least, LCOS is highly insensitive to the crossover rate. This is because the cost of rebalancing, which is crossover remediation, is so low. Again, that's only the cost to recharge the system from the inefficiencies of self-discharge upon crossover. This has an interesting implication, which is to say that improvements in membrane selectivity to reduce crossover are likely going to be ineffective for reducing LCOS and actually could be detrimental if it results in an increase in the price of the membrane itself. We also considered some practical sizing considerations. A capacity rating for a flow battery, in this example that will have 10 megawatt hours with a 5% tolerance, it can be maintained via a combination of two factors. One, the frequency with which you choose to rebalance or how high you set your capacity limit, and two, oversizing of your battery's capacity so that you can allow for more fade to occur before requiring rebalancing and other maintenance. The second option gives you a large design space over which to optimize, balancing the trade-off between the increase in upfront cost as you scale the electrolyte and the reduction in maintenance costs over the lifetime. To determine what the optimal balance is, we define an oversizing factor, which determines how much to scale the capacity, to oversize it such that a lower capacity limit of X, which is the denominator of this term, is equivalent to a 95% cutoff of your nominal rating. So looking at the left plot, we found that oversizing, shown here by the green line, significantly reduces the LCOS from the base case of solely using rebalancing and servicing to maintain the nominal rating, which is shown by the dashed line. On the right plot, we do see that this LCOS reduction does come at the trade-off of non-negligible increases to the capital cost, though. In the optimal case, this is around a 20% increase. That upfront cost increase, while beneficial to the LCOS, is important to consider outside of this analysis because it adds to the investment and financing concerns for the system. Increases to capital costs, even if they reduce the LCOS, is still a concern, and electrolyte leasing is an emerging market meant to reduce the upfront cost. Details about the leasing scheme are really limited at this point, but we do know it obviously leads to a significant significant reduction in the upfront cost, which approximately would be equal to the electrolyte cost, in exchange for an annual payment, what we'll call here a leasing fee. This scheme shifts the capital expenses to operational expenses, which lightens the burden for the buyer and reduces the risk for the investor. The appeal of this approach is dependent on the price of vanadium, though, because if vanadium is really cheap, the scheme will only be attractive to a customer if the annual fee is also sufficiently low. Thus, for our analysis, we vary the price of vanadium and back out the maximum annual leasing fee that can be charged by a lessor such that the LCOS of leasing is the same as that without leasing. Thus, we're basically setting an upper bound for the fees that a lessee should accept. And this is a function of discount rate. And we can also back out the rate of return to the lessor under each scenario, which we see are fairly sizable, implying this might be beneficial for the lessor as well, which makes sense because we do know this is an actual emerging market, though we note that the realistically acceptable magnitude for the rate of return in this unique and emerging market is still unclear. Similarly, it's unclear if the upper bounds that we've solved for here for the leasing fee align with reality. Though there is one transaction piece from Professor Skylas Kazakos at the University of New South Wales, which mentions an annual fee equal to 10% of the electrolyte cost. This may be informed by inside information or may be a total guess, but we do note that leasing fees of this magnitude fall below all of the maximum fees we have backed out as worthwhile for a lessee, meaning that if 10% of electrolyte cost is a realistic magnitude for the fee, this would indeed be a beneficial arrangement for a lessee. In conclusion, levelized cost of storage can be used to optimize operating practices for vanadium redox flow batteries, and it's also a good technoeconomic metric to accompany capital cost that captures the effects of changes in performance and cost across the battery's lifetime. Though we want to note that the comparison of LCOSs across technologies is dangerous unless application and use case are properly handled. These types of analyses are necessary to make the case for emerging technologies beyond lithium-ion. For example, with the case of vanadium flow batteries, the technology is actually fairly advanced at this point. One of the major barriers to large-scale deployment for it is financing. So we need to start creating better technoeconomic arguments to drive the deployment of these newer emerging technologies. And with that, I'd like to thank you all for coming and listening to this talk. I'd like to thank my advisor, Professor Brochette, my research group, as well as some notable alumni, my collaborators, and my funding sources. Thank you.